Our final lesson from Unit 2 is going to deal with gravity and universal gravitation. Now, we talked already this semester about mass and weight and the difference between the two. Mass, remember, was a measure of inertia, and weight was gravity's effect on the mass. Here we can see the difference between an Earth, a moon, and deep space. On the Earth, a 2 kilogram mass weighs about 19.6 newtons. On the moon, a 2 kilogram mass weighs 3.3 newtons, and in deep space, where gravity is very, 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 very small, the 2 kilogram mass weighs 0 newtons. So the idea is the mass stays constant. What changes is the weight, and this is because of the change in gravity. A smaller gravity gives you a smaller weight, but the mass remains the same. Newton's law of universal gravitation explains to us why this is the case. Newton's law is F equals big G m1 m2 over d squared. Big G is the universal gravitation constant. It's 6.67 times 10 to the minus 11th Newton meters squared over kilograms squared. M1 and M2, these are the two masses. Here in this case, you can see the big mass and the small mass. The distance squared is how far apart the masses are from one another. That would be d squared, or in this case, the radius. So the force between these two objects, the gravitational force between these two objects, are made up of all of those things. Now, Newton didn't know about big G. All he knew is there was a relationship between the two masses divided by the distance squared. And you'll see in physics there are a lot of what we call inverse squared laws, where the distance squared in the denominator is going to be very crucial in determining the force. Here's an example of how the distance squared works. If we look at our formula again, as these two masses get further apart, you can see that the distance squared is inversely proportional to the amount of force. So as the distance squared gets bigger, look how much smaller the force gets. This is also because it's squared. If it was not squared, it would be a straight line. But since the distance is squared, since this is an inverse square law, we get a parabolic shape to our graph. So just remember, with Newton's law of universal gravitation, the force is directly proportional to the product of the masses and inversely proportional to the square of the distances between the two masses. As a satellite or the moon goes around the Earth, or in this case, a planet goes around the sun, what happens is, as it gets further away from the sun, it has less gravity. That means the object goes slower. When it gets closer to the sun, you can see by the red velocity vector the object is going faster. And this is due to the inverse square law. The path of an object around the larger object, or what we call satellite motion, is an elliptical path. As this object goes around, the velocity is always parallel to the path at every single point. We call this a tangential velocity. A tangent line in geometry is a line that only touches a circle at one point. It doesn't intersect the circle. It's parallel to the circle at one point. So as this satellite goes around the ellipse, the velocity is tangent to the elliptical path. And if the sun were to go away in this case, the object would fly off in a straight line wherever it's at that ellipse. This is what causes the Earth's tides, this idea of gravity. So as the moon goes around the Earth, right, as it takes its elliptical shape, you can see it creates a tidal bulge due to the fact that water is not a solid. Water can change shape. So as the moon moves, you can see the tidal bulge move. Closer to the moon, the tidal bulge is greater because gravity is greater. Further from the moon, the bulge is greater too because gravity is less, so the water kind of falls away. And you can see the two low tides are going to be perpendicular to the moon. So the moon creates the Earth's tides. And then the rotation of the Earth, you can see as you rotate around the Earth, you're going to hit a high tide, a low tide, a high tide, a low tide every 6 hours because it takes 24 hours for the Earth to rotate the whole way around. And this is why if you go to the beach and you look at the tide schedule, it's not the same every day because the moon is revolving around the Earth, which changes the position of the tidal bulge every day. While we're talking about gravity, we'll talk about center of gravity. It relates to gravitation because we say that the force between the two objects occurs at their center of gravity, and the center of gravity is the midpoint or the average sum of the mass of the object. So here we have four general shapes. We have a regular circle. You can see that the center of gravity is in the center of the circle. We have a hollow circle like a car tire. Here the center of gravity is in the empty space of the car tire or the hollow circle. The center of gravity does not have to be located on the physical object. Here we have a square right in the center, and then we have a triangle, which would be close to the center. It's about 2/3 of the way up. So one thing you need to remember, this is the average position of the mass, where the mass is concentrated. It does not have to be on the physical mass of the object itself. If we're trying to find the center of gravity of an odd-shaped object, what we want to do, you can hang it from any point. So here in this picture, you can see we just hung it from two different points, and where those points all intersect, that's the center of gravity, which is also the balance point. So if you hung it at 1 and then hung it at 2 and put a mark at that point, you could balance that object on your finger at that point. That's the center of gravity. If you take a meter stick and you put your finger at 50 centimeters, which is the midpoint of the meter stick, you'll be able to balance the meter stick. So the center of gravity is the object's balance point. Stability is the act of being balanced. Here are some balanced rocks, and this is an actual photo. They get them to balance. They take their time. They're very steady-handed, and all they're going to do is line up the center of gravities of all the objects. So even in your regularly shaped object, the center of gravity, if you draw a line straight down through these rock formations, it would be a one straight line where all of their center of gravity is lined up. So stability is the act of being balanced. You have to have the center of gravity over the base of the object for it to be balanced. Once the center of gravity falls outside the base of the object will topple over. This is why athletic stances have you spread your legs wide and get down in a crouched position, because now you've widened your base and lowered your center of gravity. It's harder to get your gravity outside of your base now. If you stand up straight and put your feet together, now you have a high center of gravity, and if someone pushes you, it's easy to get that center of gravity outside your base, which causes you to fall over. A tightrope walker uses that pole. The pole actually lowers its center of gravity, and the pole, you can't see it real well in this picture, but it drapes down below the wire in most cases, and this lowers the center of gravity of the system below the wire. So this makes you very stable. So now all you have to overcome is your nerves as you walk across here, because your center of gravity is going to be directly below that wire, and you are going to be very stable as you walk across.